Lesson 71 is our first lesson on solids of revolution, and we're going to have a few different lessons on this and a few different methods for actually finding the volume of these solids of revolution. This one is called the disk method. It's the most simple, and we'll take a look at that in this lesson. So first, I wanted to just show you a little bit of an animation of what's going on here. So let's take a look at this program. Here we have the function y equals 1/2 x squared plus 3, and I'm only having that on the domain from -3 to 3. So that's the graph of 1/2 x squared plus 3. And we're going to look at this solid of revolution that is going to appear. And what we're going to do is we're going to revolve this function around the y equals 0 line, which is actually the x-axis. So let's go ahead and do that. We can hit this revolve button. And so it's taking that graph and wrapping it around the x-axis, as you see there. So you have this shape that's formed, and this is called a solid of revolution. Now, what we're going to be dealing with is actually if this whole thing was filled in and there wasn't these gaps in the middle. So there is a solid of revolution. There's one solid of revolution. We can change this up to do different solids of revolution. Here I put a different graph in. This is 3 to the x power plus 2. So it's an exponential function. This time I'm just going for the domain of -3 to 2. And we can do the same thing. We're going to revolve this around the line y equals 0, which is the x-axis. I can hit this revolve button, and it will take this graph and it will revolve it around the y-axis. The x-axis, and you can see it's kind of like this interesting looking doorknob maybe, but we have the graph of that there. And so that's another solid of revolution. And here we have the graph y equals sine of x. We're going to go from basically -2 pi to 2 pi. And I'm going to start revolving this around, again, the x-axis. So here we go, revolve it around. I'm going to go ahead and pause here so we can see what's happening. So we're taking this graph, it's getting revolved around the x-axis. And we'll go ahead and finish that off. And you can see we have a bunch of these little shapes here. That's where each of those sections gets revolved around. So let's reset our view here. And we have y equals sine of x. And so what we're going to do with these solids of revolution is we want to find the volume of them. So this gives us the volume altogether. Let's go ahead and just change this really quickly. Let's just get one section here of our sine. So that's from 0 to pi. So we'll go from 0 to pi. And so that should be accurate enough for us. So we're going to set our function there. There it is. Let's go ahead and revolve it around the axis again. You see it revolving around there. And we have that solid there. And we see the volume here says it's 4.934. Surface area is 14.422. So obviously this program can find that for us, but what we're going to be doing is we're going to be finding the volume of these solids of revolution over the next few lessons. So now you know what we're looking at by looking at that animation. Here we have the same idea. We're going to take some region, so this will be some function f between two values. Sometimes we're given those values, sometimes like on that last one that we did of sine, it's just wherever it hits the x-axis. And we're going to take this and we're going to revolve it around, in this case, the x-axis. You can also do the y-axis. And if you revolve this around the x-axis, you would get this shape. And what we're going to do, it's going to be similar to what we did to find the area under a curve when we first started that. We can think of breaking it up into all these small disks. So notice this shape is an approximation of this shape here, and we're going to find the volume of each of these, what we call disks, and those disks are actually cylinders. And so the way that we ended up finding the volume of a bunch of areas under a curve was to use the definite integral, and that is what we're going to do here, the same idea. In this case, these are cylinders, so we know that the volume of a cylinder, is the volume, the area of the base, which is a circle, so it's the area of the base times the height, and the base is a circle, so pi r squared times the height. And then what we do here is we're going to relate this to our volume over here. Our radius for each of these disks is just where it reaches on the function. And so our radius is actually the value of the function. So we put f of x, so pi is still just pi, obviously. So volume equals, the radius ends up being just the value of f of x, so the value of the function, squared, that's our radius, and times the height is our change in x value here. So we have all these little heights of our cylinders. Think of if they're sitting this way, it's easier to see that this part is the height, and those heights are just going to be our change in x, or as we put it, we put dx. And so to find the exact volume of a planar region revolved around the x-axis, from the x values a to b, you take the definite integral from a to b of pi times the radius squared, which is the function itself, dx. So it's as simple as that. And so what we're going to do is we're going to take a look at some examples here. It says find the volume of the solid formed by revolving this triangular region about the x-axis. So what region? So let's see what region they're talking about here. So we have this triangular region. We're given this line here, y equals negative x plus 1. Slope of negative 1 crosses the y-axis at 1. And we're revolving around the y-axis. So we know that the exact volume is going to be the integral from a to b. Well, in this case, it's from 0 to 1 of pi times the radius squared. Well, our radius is the value of the function, so our function here is negative x plus 1, so negative x plus 1 squared dx. And we want to integrate this. Well, it's a pretty simple integration. We can bring the pi out because that's a constant. It might help us to multiply this out. You could probably do it one of two ways. Let's go ahead and multiply this out. So we get from 0 to 1, this will be x squared minus 2x plus 1 dx. And now we can integrate. That's going to be pi. Integrating this is 1/3 x cubed minus x squared plus x, evaluated from 0 to 1. Plugging in 1 gives us 1/3 minus 1 plus 1. And then we're going to subtract, plugging in 0, which just actually gives us 0. And so we have that the volume of this will be, so this is 0, so we got pi over 3 units cubed. So make sure you realize it's units cubed, so pi over 3 units cubed. Well, this actually is just a cone, and we know the volume of a cone, so let's check this just thinking through geometry. The volume of a cone is 1/3 pi r squared h. Well, we have 1/3 pi. What's the radius of this thing? Well, the radius is 1, so 1 squared, and our height here is also 1 times 1. And so we do see that we have the correct answer because this is 1 times 1. So 1/3 pi, or pi over 3 units cubed. Obviously, if we think about this, the geometry way is easier to get this one, and that's because it was a shape that we're familiar with. Once we get away from having a line here, we wouldn't necessarily have a shape like a cone that we're familiar with. So this next one, find the volume of a solid formed by revolving about the x-axis, the region bound by the graphs y equals e to the x, x equals 0, x equals 1, and the x-axis. So we are rotating something about the x-axis. We can draw a quick sketch of this. This is e to the x, so we would be, it's an exponential function. So there's e to the x. It's saying take it from 0 to 1. And so this shape. And the other region boundary is the x-axis. So we're taking this and revolving it around the x-axis. So we're taking this planar region revolving around the x-axis. Well, same idea. Make sure you know this concept of the volume. It's going to be the integral from a to b, which in this case, again, is 0 to 1. Pi times the radius squared, which the radius is the function, so this is e to the x squared dx. And so that is the integral that will find us that. We can bring the pi out here from 0 to 1. This is e to the 2x dx, and we want to integrate that. So let's think through this. We got pi, and then the integral e to the 2x, but thinking through what we might have to change because of the chain rule, we probably need a 1/2 here. Evaluate it from 0 to 1. Let's just check to make sure this is right. So we want to check our integral. So we're taking 1/2 e to the 2x, and we want to find the derivative or the differential of that. So obviously the derivative of e to the 2x is e to the 2x. So we have our 1/2 still, sorry. Still got the 1/2. Derivative of e to the 2x is e to the 2x times the derivative of what's inside, so times the derivative of 2x, which is 2. They cancel. This is what we wanted, so this is the correct integral, and now it's just a matter of plugging in our values. So we have pi times 1/2. Sorry, we want to plug in 1 first. Plug in 1, we get e squared, and then we want to subtract. When we put in 0, 1/2 e to the 2 times 0 is e to the 0, which is just 1. And so what we could do here, if we want to keep an exact value, we could factor out a 1/2. So we have pi over 2 e squared minus 1 units cubed. If we wanted to get an approximate value, you could plug that into your calculator, and you get approximately 10.04 units cubed. Looking at the next one here, this is going to be a little bit different, so we're going to have to think through this a little differently. Find the volume of the solid formed by rotating about the y-axis. So up until now, we've been rotating about the x-axis, but we're going about the y-axis. The first quadrant region, bounded by the line y equals 3, the graph of y equals x squared, and the y-axis. So let's go ahead and take a look at this graph. Here's our x-axis and our y-axis. We want y equals 3. 1, 2, 3. We need this horizontal line to be one of our boundaries. Y equals 3. Y equals x squared, which is a parabola. So it goes through 1, 1, and then 2, 4. And then we would have it on this side too, but it actually says the region in the first quadrant, so we don't need to worry about it over here. And the y-axis, so here's our y-axis. So we're going to take this region in here, and we're going to rotate that about the y-axis. So we're going to rotate about the y-axis. All right, so we're going to need to think about this a little bit differently. We're not going to be doing this in terms of x here. We need to do this in terms of y, because we're going to be rotating, and we're going to be looking at rotating around the y-axis. So we're going to change this up a little bit for rotating about the y-axis.
This is Maddie. This is Maddie. I like math.
So our volume, we're going to switch this up a bit since we're going around the y-axis, is the integral. So this is going to be in terms of y. So we're going from 0 to 3, y equals 0 to 3, pi. This time our radius is going to be this way, so it's whatever x is equal to. Because see, we're coming out, our radius is a horizontal distance, which is an x value. So what we want to do is we want to figure out what does x equal. So we have to take the square root of both sides, and we know x equals plus or minus the square root of y. Now we only want the first quadrant region, so we don't need this minus sign. So we just know x is the square root of y. So we're going to take our function, which in this case is not a function, it's in terms of y. So we got square root of y squared, and then dy. And that will be the integral we want to use to find this volume, the volume of this solid rotated about the y-axis. So when you're rotating about the y-axis, using this disk method, you want things in terms of y. So your variable here, dy, and then these values should be your y values. And then you can integrate this. First we'll simplify it, so we're still going pi. We can put the pi out here since that's a constant, 0 to 3. Square root of y squared is just y dy, and then this one's really easy to integrate, so we got pi times 1/2 y squared, evaluated from 0 to 3. Putting the 3 in, we get 9/2, so we get pi times 9/2, minus putting in the 0 is obviously 0 squared 0. So our answer is 9 pi over 2 units cubed. And that is the volume, and this time we went around the y-axis. We have a couple more that we want to look at. This one says, find the volume of a solid formed by rotating about the y-axis. So we're doing the y-axis again. So this actually isn't going to be in effect. The first quadrant region of the circle whose equation is x squared plus y squared equals 9. So we need to be familiar with the equation of a circle. So x squared plus y squared equals 9 means our circle is centered at 0 with a radius of 3, because we think 3 squared. And so we got 3 and 3. It just says the first quadrant, so we're going to try to sketch in this quarter of a circle here. And then this is going to be rotated about the y-axis. And so if you think about this, this is going to be a hemisphere. Try to sketch it in here. So this is like half a sphere here that we're going to be finding the volume of, which will give us a clue to what's going to be coming up in the next example. So we want to find the volume. And again, we're going about the y-axis, so we want to do this in terms of y. So we're going from 0 to 3, because we're really taking this region in here. 0 to 3, pi times the equation we're working with, squared, and it's going to be dy. Well, if we think about this, we're taking this radius. So this is our x value, so we need to solve this for x. So we have x squared plus y squared equals 9. Subtract y squared and take the square root of both sides, so we get the square root of 9 minus x squared, y squared. And we don't have to do plus or minus, we just want the positive part because we went over here. It's only in the first quadrant. And so this is our equation that we're working with. So we got the square root of 9 minus y squared. And then we can simplify this a little bit. We can bring the pi out here. This is integrated from 0 to 3. The square root and the squared cancel, so it's just 9 minus y squared dy. And again, not too hard to integrate. So we get 18 pi units cubed. This last one is a great one because it's actually going to help us find the formula for the volume of a circle. So it says find the volume of a solid formed by rotating about the x-axis. The region bounded above by the circle whose equation is x squared plus y squared equals k squared. So just a general radius k. We could have used r if we wanted to. And below by the x-axis. So the region above is going to be bounded by x squared plus y squared equals k squared. So that's going to be a circle that goes through k and negative k. So we're going to take this half a circle and we're going to revolve it around the x-axis, and we want to find that volume. So since we're going around the x-axis, we are actually using this one right here. So we are going to integrate from negative k to k of pi times our function squared, well, dx, and our function is f of x, so we actually want to solve in terms of x, so we want to solve for y. So we would have y squared, so subtracting x squared from both sides is k squared minus x squared, and taking the square root of that, we get y equals the square root of k squared minus x squared. So, and we can put that in. K squared minus x squared. Remember, k ends up, that's just a constant. And so let's bring the pi out here. We got negative k to k. The squared cancels with square root, so we have k squared minus x squared dx. And then we can go ahead and integrate this. We have pi times, and we want to integrate. This is just a constant, so we have k squared x minus 1/3 x cubed, evaluated from negative k to k. So we have pi. We will put in k first, so we have k squared times k, so k cubed, minus 1/3 k cubed. Putting k in there. And now we're going to subtract when we put in negative k. So we have negative k in here will give us negative k cubed minus negative 1/3 k cubed. A lot of grouping symbols there. We have pi times, well, k cubed minus 1/3 k cubed is 2/3 k cubed. And then this is negative k cubed plus, so we have this minus sign, so minus negative k cubed plus 1/3 is negative 2/3 k cubed. And we see by adding those together, we get something that should be familiar to us. We have pi times, this is minus and negative, so this is like adding, 4/3 k cubed. Rearranging that to something we're more familiar with is we get 4/3 pi times k cubed, where k represents the radius. And so we just found the volume of a sphere, and we showed why the volume of the sphere is the equation that we learned a few years back in geometry.